Hi. The second topic in this course will be focusing on relations. In the previous segments, we discussed sets, which are how we represent collections of things mathematically. Now we move on to relations, which are the mathematical way of representing connections and relationships between things. As you will see, relations are really a particular kind of set themselves, so everything we talked about in the context of sets applies to relations as well. Mathematical relations are about connections between objects. If the objects are whole numbers, a relation we might be interested in might be whether one number evenly divides another, is greater than another, or prime to another, for example. Relations between sets might be whether they include one another, or whether they are of the same cardinality, or whether one might contain more elements than another. Relations between people could represent their connections as customer and client, parent and child, and so forth. In the following, we'll mostly focus on relations between two things, although we will occasionally also allow more than two things be connected. In many cases, the things related to one another by a relation assume particular roles in it. In a relation that connects seller and buyer, for example, it is of course important which of the two people thus connected is the seller and which one is the buyer. And the same applies to other relations such as parent-child, or in the case of set inclusion, which is the subset and which is the superset. For this reason, we cannot just represent a connection between two things as a simple set containing both of them, since we want to be able to distinguish, for example, which of the two is the seller and which is the buyer. Therefore, we need ordered pairs of things. That is, pairs that have a distinct first and second member. This is then the focus of our first segment, ordered pairs and sets of ordered pairs, also known as Cartesian products. We'll write ordered pairs, or just pairs for short, simply as two values separated by a comma and closed in parentheses. The defining property is that two ordered pairs are equal if and only if their first, or left, components are equal and their second, or right, components are equal. We also say in that case that they're position-wise equal. This means that any such ordered pair is different from a pair with the same component but flipped, unless of course the two components are equal to each other. This easily generalizes to things with more than two components, which we call tuples or n-tuples, to emphasize the number of components they have. Pairs then would be a special case of two tuples. A Cartesian product is a set of such tuples. More specifically, the Cartesian product of a number of sets A1 through AN, they can all be different sets or not, it does not really matter to this definition, is the set of all n tuples such that the kth component is an element of the kth set AK. In other words, it is the set of tuples representing all combinations of elements from the sets A1 through AN. The cross operator is spoken cross, or occasionally times, as an A cross B or A times B. When the original sets in the Cartesian product are all the same, we can also use exponent notation. A square is the same as A cross A, the set of all pairs with elements from A. A to the n is that of all n tuples with elements from A. Note that when the two sets of a Cartesian product aren't the same, the order in which we use them in a Cartesian product matters. A cross B is the set of all tuples where the first or left component comes from A and the second or right from B, while the pairs in B cross A have their first component come from B and their second from A. So the resulting products are different sets. Generally, when multiplying multiple sets into a Cartesian product, we won't be fussy about the order in which they are built. For instance, what do these two Cartesian products look like? The first is a 6-element set of ordered pairs combining every element of AB with every element of 1, 2, 3. The second is the set of all pairs of positive natural numbers. Note that, at least for finite sets, it is the case that the cardinality of a Cartesian product is the product of the cardinalities of the sets in the product. Just as there are 6 combinations of elements of a 2-element set with those of a 3-element set. We shall see later that this rule also extends to sets with infinitely many elements.